Hey everybody, this is Larry, this is me going Q4 of the weekly contest 484, maximum bitwise and after increment operations. Hit the like button and subscribe button, join me on Discord, let me know what you think about this one. So this one, honestly, I did have a general idea immediately. I still ended up taking a while just because I kind of couldn't figure out the math precisely, to be honest. And I got two wrong answers as a result of it, as you can see. Honestly, sometimes, you have to be honest with yourself. And for me, I don't know that I could have gotten this one without two wrong answers. This idea is new to me. And even though I got I got partially the idea of the final answer, which I ultimately got, but I needed a little bit more, and I was kind of missing that for sure. And so I don't know if I could have gotten it without two wrong answers. Maybe one wrong answers anyway. Maybe I could have gotten it without wrong answers if I just spent like a long time coming up with test cases all the time. But then at that point, I'm spending longer than 10 minutes, which is the number of wrong answers that I got, right? So anyway, okay. So the first thing that I wanted to do for this one, right now I'm just gonna go over my thought process of how I attempted to solve this problem. I think it's more interesting. I mean, if you wanted to just see the solution, you can just see the solution. You don't need me for this. So that's my thought process, right? First of all, we're trying to maximize the result of a bitwise operation, right? The way that I always think about these is that there is always going to be some sort of a greedy component. And why I say that is because, if I'm thinking about it in terms of bits, let's just say you have, let's just say you have like spaces for bits, right? Then now, if this is a 1, it really doesn't matter what the rest of it is, right? It matters, but if this is a 0, then it doesn't matter because this number is always going to be bigger. So when I say greedy, at the very least, it's this kind. So I was going down this line of thought of, well, how do I check for this? And this part I did get very quickly in that, okay, well, what if we test it for 1, right? Oops. In a greedy way, what is that? In a greedy way, we just go, okay, let's test, almost like, if you ask me, and it's almost similar, at least the way that I think about it, in like almost like a digit DP, in that we just kind of greedy on the first digit, right? We go, okay, if this is 1, what happens? Well, or like, how do we get the answer to be 1? And then this is the part of the problem that is actually related to this problem, right? Which is that, okay, well, if this is 1, then that means that, well, we have, let's just say, n numbers, but we need at least m of them to have this, to have 1s, right? Because, if you have at least 2 1s, then the bitwise n would be, 1, right? Kind of, right? But that's the kind of what I've started thinking of. And then the second component is that, well, let's say we really need m is equal to 3, but there's a 0, then we can increment, maybe we can increment in a way such that we can make this a 1, right? And then that's where I was going through, like, now you see my progression, like step by step, right? I start by asking myself, okay, it's gonna be, oops, I meant this to be like this. I wrote this to be greedy, right? Like I want to optimize for this is equal to 1, and then what do I need? That means that I need m 1s in the result and the bitwise for that, and of course we go from the most significant bit first. And then what does this mean? This means that we're trying to figure out the cost of making at least m of these have these bits 1, and then what does that mean? And of course that means that also, I kind of hand waved it a little bit. Let's say you have multiple 0 candidates, then now, well, if you have multiple candidates and you need m is equal to, say, 4, then how do we get 1s in here, right? Well, we're also trying to do it in a greedy way, which is that, well, maybe it costs a here, maybe B for this number, C for this number, D for this number. Then in a greedy way, if M is equal to 4, meaning that we have to pick 4 numbers, then we just choose the min of these 4 numbers. And then that's where you may have ideas about a heap after that, because I'm like, okay, well, in this case, then we just kind of keep track of a heap of size 4. So then we take the the cheapest 4 to calculate, to make this a 1. Because the cheapest means that we are now have more to use for later, right? And that's basically the idea. And I do this 1 bit at a time. And it kind of comes out a little bit like a binary search. And you can think of it that way anyway. I mean, you know, all these constructs are just visualization tools to help you problem solve. Don't lose sight of it. But I don't think of this as binary search, even though the code is very similar, just because, yeah, if this is a 1, then we just go on to the next digit, because we can assume that, because the idea here is that with this being a 1 and we have whatever we need to satisfy to keep it a 1, that means that the rest of this stuff, like I said, it doesn't matter if they're all 0, it is still going to be bigger than, you know, all this stuff, right? Because it's bigger than that, then now this would be good for you. But then, you know, in a greedy way, we just now let's try see if we can make this a 1. Yes, no, maybe, right? And then try to make this, and then so forth. The only other kind of tricky part and actually everything I've said so far up to here, for me anyway, I mean, this is just my disclosure in case you want a relative, you know, like what I struggle with, right? And you can watch the live portion, you'll see it. You know, there's no whatever about it. But actually, like everything that I've said so far, I've gotten very quickly, actually. I don't know, you have to watch the video to see how fast, but relatively quickly. The part that I struggled with was actually this next part, right, is that actually, the question is that now, okay, so let's say you're testing, let's say you're testing a number, right? Let's just say you're testing this prefix, and you have a number that's like or something, right? Then what is the cost to get this number from, or like what is the cost to quote unquote match these two, right? And to match these two, keeping in mind that you can almost look at this as a requirement for each bit, right? Because and you know, maybe the ones where we haven't gone yet, it's okay, there's no requirement. But 0 doesn't mean that you need a 0. It just means that you know, we don't have no requirement there. But a 1 in a digit means that every number that we check against has to have a 1 in that digit, because that's what a bitwise AND does. So yeah, so then now, you know, as you can see, this is satisfied, this is satisfied, this is not. So in order to kind of well, make this 0 into a 1, we would increment, you know, increment. Well, I'll spoil it. You just have to add 2 to basically, you know, this 0 turns into 1, and then 0 after 2. You have a carry 1, and then this turns into 1, and then you get this, right? Hopefully, I don't have to explain how to, you know, add binary numbers, but you get the idea, right? So then now so adding 2. So that means that this cost is actually equal to 2. So what I struggle with is actually trying to solve this in a fast way. But I think now that I said it like that, I mean, I had some idea of what I just said, but I didn't really articulate this very well, like internally, when I was thinking through this. But yeah, and of course there is stuff like, you know, like if this is a 1, that's nice, but it actually doesn't, like, you know, it doesn't make it worse, but it also doesn't change the answer for stuff to the right? So that's kind of the idea, and that's the tricky part. It turns out the idea to do this is just 1 bit at a time, going from left to right. Because then now, let's just say you have 1, okay, fine, requirement met. This one, there's no requirement, it doesn't really matter, let's just say it's 1. But if this is 0, then now you know that you can, another way of thinking about it is that at the very least, you know that you can add this number, right? In binary, of course. So maybe, is that 16 or 32? 1, 2, 4, 8, 16, right? So 16. So you could add 16 to make this from 0 to 1, right? And then in the next number, same thing. Maybe if you had 0, then you have to add this number. So then now 16 plus 8. But let's say this is a 1, right? What does this 1 mean? This 1 means that, well, we don't need to add 24 anymore because 4 of them is taken. So then we only need to go to 20 or whatever, right? I don't remember the number. And then so forth. So that's kind of the idea. And honestly, it took me a long time to kind of really come up with that plan. Even though now it's one of those things where you say it out loud, but I was gonna say it's one of those things where you say it out loud, it sounds so much easier, and I kind of feel dumb for not getting it faster. But then it's also part of what math is, right? When you know the answer, everything seems obvious and trivial. So I don't know. Anyway, this is my code. So let's go over it really quickly. So R is the answer, right? What we return. We actually don't use this because I was doing it for some other things as a hack, but it didn't work. So yeah, let's give it a YOLO submit right real quick just to make sure that this is still yeah, okay. But yeah, so for each digit, and keep in mind that we're doing most significant bit first, we try and this is structured like exactly like a binary search now, right? Meaning that yeah, if we made this bit 1, can it be true? If it's true, then we always take it because this is in a greedy way. And then this is the target, right? Needed basically as I said, because you only need m things, right? And because you only need m things, what I did is that for each number, I calculate how much you need to make that number into the target, the pattern, the target pattern, right? And we'll go over that in a second. And then we just take the smallest m. We sort it, we take the smallest m, and then check that it is less than or equal to k, right? Because k is that number of operations that we get. Of course, you can use a heap here, by the way, and maybe should have to make it instead of n log n, it'll be n log m with a m min heap, right? Or max heap. No, yeah, you would use a max heap, so it'll be n log m with a max heap. But log n and log m is not significant for the most part, or on average maybe. So you know, I don't know. It's fine for now, just for implementation wise. But yeah, so that's basically that part. Oops. But otherwise, then now for each number, there are two things. If x is less than the target, which we have here, you just do the subtraction because that means that it's smaller. That means that you just kind of keep on incrementing until you have enough numbers. You don't even need this if statement now that I rewrote this part, but it is a little bit faster, right? Because it's just a subtraction. Otherwise, it is what I said, which is that there's a delta. If we need this, but we don't have it in the number, then now we have to add that many numbers to get to the to get to this number, right? That's the number of additions you need to do. Otherwise, if the delta, if we can use this delta, and this is 0. This is 0 because we just don't need it. And this is greater than 0, then we should use it, which is what this is doing. So you have add and subtract, and then at the end, after processing all the number, then now you have the delta, and that's it. I want to say it's straightforward, but you know, it's like I said, if you know the formula, it is easy. So, but and obviously, you know, the hard part is coming up with that formula. I don't think this is a standard thing, but maybe I'm wrong. Maybe it is something that people know, but I didn't know it anyway. So at the very least, I'll show you that it is possible to come up with it with a couple of wrong answers. But yeah, that's it. That's all I have for this one. This is only like a short 28 lines of code, and I probably could have made it even tighter if I really wanted to. So yeah. Yeah, that's it. That's all I have for this one. Actually, let's go over complexity really quick. This is clearly an over B loop, right? But these things are always tricky to do complexity because we can definitely fall into a rabbit hole. Because for example, like, well, what's the cost of a bitwise OR operation? Is it O of 1 because it's one bitwise operation? Or is it, we have B bits at the same time, so is it O of B? And there's a shift. Is the shift O of 1 or O of B? Or, like maybe it's optimized on the hardware level, right? Because this is just a bit shift that, and you can even imagine that, single bit things may already be cached somewhere, or not even cached, but just like hard coded somewhere on a hardware bench somewhere. I don't know, right? There are a lot of things that can happen. So it gets a little bit nuanced if you really want to be pedantic and precise about complexity. But I say that to say that you can do it, but I don't know if it's worth it. But yeah, let's just say this is O of B, and we call it good O of B times, and for each B, it takes O of n times O of B, and plus n log n. So it probably gets dominated by the n log n anyway versus B. Well, B is at most log n. No. Well, that's not true. Well, B is not at most log n. It's the other way around. Log n is at most B, right? That's what I meant to say. I was like, that doesn't sound right. So I don't know. You can take it as you will. And the sum is trivial. I mean, it's just linear. And that's it. That's all I have for this one. Let me know what you think. Thanks for watching. And you can watch me solve it live in the contest now. Alright, and here we are at the hard. How are we doing? I usually check how we're doing after, just to kind of see, well, how we're doing. People seem to do it pretty fast, so we'll see. Alright, K and M. I most can choose any index I and increase nums of I by 1. Return an integer denoting the maximum possible bitwise n of any sub. What? Okay. Double check the constraints. Okay, so they're nothing crazy. Let me reread it. One operation, choose any I and then increase it by 1. Return an integer denote the maximum possible bitwise n of any subset of size m after performing up to k operations optimally. Okay, so m is equal to 2, means you get to choose 2. And again, you can choose almost all of them. There are any bitwise things. K being 10 to 9 is interesting, maybe. Okay. And n is decent amount. So we want greedy. Maybe. I mean, we do want greedy. That's the thing. What do we want exactly? Well, we want greedy, but how do we allocate the K? No, allocating K on the greedy is fine. Ish. Maybe? Do we always greedily? Yeah, maybe we do. Just one bit at a time. Sort by trying to think. But it's greedy. I'm just thinking through all the scenarios, right? So you never, in terms of preserving k, you never take a 0 to go to a 1, because that would just always be more expensive than having a 1 already. Can I binary search? Is it binary search? Just one bit at a time? I mean, it's like binary search. I mean, it is binary search, but it is just one bit at a time, right? And then we just keep sorting. And there's only 32 sort of n, so I think that should be fine. Okay, yeah. Okay, yeah. Let's just continue, right? Let's keep it consistent, say. Maybe we can end with numbers, but it shouldn't matter. So then now, how do I do the math on the prefix? So then it is the substring adding to this number, right? So then that means that the prefix how do I clean the number? So everything that's not on the bits that we care about, but the lower bits matter in the number of things that we need to do. Just that the high bits don't matter, right? So anything that's bigger than the biggest bit don't matter. I think if it's an else, then we just take away that bit from everybody to do the math correctly. Maybe. Yeah, maybe that sounds right. Something like that. Okay. Yeah, that's fine. Okay. Okay. So then now, this should match the prefix. So if x is greater than target, then it just means that, yeah, that means that we're good, maybe? I'm not quite sure about this one. Otherwise, then, something like that. Well, maybe that's not quite right. Oh, it's the other way. Yeah, that's why. 422. I mean, alright, it's not right, but it's an idea. 4 is right. 4. Oh! I forgot we only need M of these. That's right. Okay. That's why I keep saying sorting and stuff, but I just forgot about the M part. Okay. So okay. Then we have. How do I write this? Needed. No, is it K? No, it's M. Yeah. Alright, 642. I don't know why I forgot about it. I structured it that way for that reason, but alright, looks okay. I'm not 100% confident about this. It's just a little bit more YOLO. And here we got it wrong, so that's okay. It's a quick one. Oh, maybe I'm off by a little bit. It tries 16. 16 as an output doesn't make sense to me though. Does that mean just double whatever? So 8 trying 16. Oh, it tries 16. It removes the. Oh, I see. My logic is a little bit wrong, at least in the greedy part, because then now it tries 16, right? But then it flips off this bit. That's why, because it flips off the other bit. It flips on the 16 bit. Then now it doesn't want the second bit, so it flips it off. But because it flips it off, it goes from now 0 to 16. Which is not right, so this is wrong. How do I? This part was always the sketchy part to me, so maybe that was. Maybe I can just do this, but maybe I could just do something like this. I don't know. Because I was only hoping to do it on the prefix, so something like that maybe makes sense. I'm not super confident, but I'm gonna YOLO submit anyway. Oof. But that was the idea anyway, right? But this doesn't make sense though. Okay, so we try the 4, which is fine. 4. I mean, it has no overlap, but 4 is fine. I don't know about this part, the 0 part. I think that's probably why. K is equal to 3 means that we take the 2 and then we just made it to the 4. But the 5 doesn't really make sense. I don't know where we got the 5 from. We tried the 4, so 4 works, and then it greedily tries to do one more. Oh, because the 14 converts to 0 from this, and then the 0 we just add 1 is what it thinks, maybe? That doesn't even make sense actually, but Actually, it doesn't make sense. I don't know. So 8 doesn't work. 4, it works for sure. Because, yeah, it works. But then now just 0, 3. No, there should not be a 5. Why? How is, where do you get the 0 from? Oh, because this number, yeah, I think this part is wrong. On the max part. I was worried about that. Because you have why is it, oh, how do I do that math? So if it's bigger, you still need the thing. Okay, so if it's bigger, you still need ones in the same place. It's not just that it is, oh. How do I do that math? Okay. So I think the idea is still, maybe I believe in it, but how do I do this math? Okay, so target X, but then what if you have the other way around? Huh. How do you do that math? Me not knowing, I think that's why I thought I could just reduce that to 0 for some reason, but that's not right. I don't know why I thought that, but that is. Do I do a DP? Do I need a DP? Because I'm thinking of something like if I have this number and then I just need well, even if I just need this number, I need to just increment by 1 so that it is a superset of this. That's fine, but how do I get this number to be 1? Oh, how do I not even this? Yes, you can take the fact that this is a 1 bit. How many bits until this is a superset of this? So that is going to be just an OR. Would an OR make sense? No, not necessarily, because in a different case, maybe we have someone like this. And then the OR doesn't make sense because Okay, so we have to do an if statement. So here to do. Okay, so then we need these 2 bits. This one we don't need. But it also kind of reinforces this if I have like okay, if I have something like this. Well, this number is then smaller, and then you have this. You just do this math, but we have someone like this. You still have to do this math on this suffix, right? I guess we can just do the brute force bit by bit. This is harder than I would have expected. I thought I had most of it, but maybe I'm wrong. Yeah, it was here, then now you need to just convert this into this, which is fine. It's not a... Does this one do anything? Why do I structure it this way? Is there another case I'm thinking of? I should have drew it out. Oh, how? If I had something like this, then this one doesn't even... How do I do the math? How do I do the math? Huh. that can be true. Just true. Maybe. YOLO. Not confident at all. Okay. I was worried a lot about this being wrong, to be honest, because I did see this quickly, but I thought maybe there'll be some edge cases, and I already got wrong answers. So, thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, take good mental health. I'll see y'all later. Take care. Bye bye.